Thomas Vidick, who was introduced by Camilo on the first lecture, is giving the series, and this is the second of the series. And it's remarkable that ideas from computability and undecidability would resolve a long-standing problem in functional analysis. And this is the second of the three lectures. And the title of the lecture today is From Non-Local Games to Undecidability.
Okay, thanks for that. Hi, everyone. So let me recap where we ended up on Monday. So I wrote maybe slightly too many things on the board there, but so what we did is that we reduced or explained that the problem of negating this constant embedding problem could be reduced to showing that two convex sets are distinct. And I announced the strategy for separating these sets, which went through showing that a certain problem is undecidable. So this is one of the sets out there, Q star of NK. So maybe I'll draw it again. These sets were subsets of 0, 1 to the n squared k squared. So for every n and k, we have such a set. I think the Q star one was the relatively simpler one. It's the one that I had drawn in blue, I think, last time. So it looks like this. Okay, so every point in this set is a vector, is a tuple of probabilities, such that each of these probabilities can be expressed as so there's an integer d there, which is ranges freely over the integers. I didn't quantify it, but it's for any d. Tau d, remember, is the normalized matrix trace in d dimensions. So it's 1 over d times the trace of the product of p and q. P and q are just projections in finite dimensions. And for every x, the collection of pxa's is what we call a projective measurement. So it just means that they're orthogonal projections that sum to identity when you sum over it. Okay, so for every x, we have a partition of identity. For every y, we have a partition of identity, and we compute the trace of their products.
And what does x and y range over?
X and y range over, thank you. So x and y range over the integers between 1 and n. And a and b range over the integers between 1 and k. So n and k are integers that are fixed. They parameterize my set. They can grow. So n is, let's say, 5, k is 5. You can just think of that. You don't need to think of bigger. And so x is between 1 and 5, a is between 1 and 5. That's it. Maybe one thing that's important to keep in mind is that so this set is finite dimensional. It lives in a finite dimensional space, and it's 5, k is 5. This is low dimensional. But each point in the set, the fact that it's a point in that set, this can be witnessed by something that's of arbitrarily high dimension. Okay, so given a point, to decide whether it lies here or not, I need to decide if there exists a d and there exists some p's and q's in that dimension, such that blah 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 each of the numbers are here. Okay, so this is what makes the set complex. And in fact, the consequence of what we're going to show is that the membership problem for this set is undecidable. So in general, it's extremely hard, given just a collection of n squared k squared numbers, to decide if it can be expressed as this. Okay, that's going to come as a consequence of what we're going to do. Okay, so then there was a yellow set, which was bigger, but we don't need it anymore because we reduced the problem to simply showing that the problem of optimizing a linear function lambda over the blue set. So this is this line in the middle here, omega star of lambda, to show that that problem is undecidable. We showed that that was sufficient because the blue set was such that there existed a very simple sequence of inner approximations to it. The yellow set, there existed simple outer approximations to it. And if the two sets had been equal, then the optimization problem would be easy, or at least computable. By the way, if anyone does like convex optimization or things like that here, this is slightly unusual situation in that in general, when you have a convex set, optimizing a linear function over a convex set, this is supposed to be easy. But it's easy when you at least have access to a membership oracle for the set. It's easy if the problem of deciding membership is easy. Here, the problem of deciding membership is not so complex. Okay, so our goal is to show the following theorem. So this we did not show, it's our candidate. So we want to show that there is a computable function that maps Turing machines to integers nk and linear functions lambda on that space, such that if the Turing machine halts then the optimum of the linear function on the set is 1, and if it doesn't halt, then it's something that's less than 1. With half, this is just by convention. It doesn't matter. It's just something strictly less than 1. So what this effectively does is that it reduces a well-known uncomputable problem. So the problem of deciding if the machine halts or doesn't halt, this is easy to show uncomputable. Turing showed this by a diagonalization argument. And we're reducing this to that problem. So because this is undecidable, this problem will be undecidable too. And as a consequence, this function, omega star of lambda, will be unknown. Okay. All right. So any questions on that? Okay, so to carry out this program, we need to be able to construct a linear functions lambda that are interesting. We need to be able to construct them that are more and more complicated to the point where we can embed like a really complex problem into just a simple question about lambda. So the goal for today is to kind of give you a little bit of ideas on where these lambdas come from. And they're going to come from two different directions. One is the theory of non-local games, which is something that comes from the foundations of quantum mechanics, let's say. And the other is complexity theory. So we see complexity theory show up halfway through the lecture and give us ideas to construct the lambdas. But for now, I'm just going to make a little bit of an aside and tell you about non-local games. So I'll define non-local games. I'll give you a famous example, which is the magic square game. We'll analyze it a little bit. And then after that, I'll go back to this and say how these games can be used to show the theorem. So here's what the game is. So I'll first give the definition, and it will be a bit, and then I'll give an example. So a non-local game. Sometimes it's also called non-local is the term that comes from quantum information. In computer science, they're called just two-player games. Non-local game is G. So it's just a tuple of 4 things. So X, these are finite sets. I is going to be a distribution and D a function. So I'll write this explicitly. So X, A, these are finite sets. Pi is a distribution on the Cartesian product of 2 copies of X, and D is a function from X cross A to 0, 1. Sorry, this is 0, 1. So that's a game, okay? So it's just given 2 sets of distribution and a function. So let me say what's the game side of this. So how do we interpret this as a game? So it's a game, this describes a game that's played by 2 players. So we usually call them, so for my experience in explaining non-local games to mathematicians is extremely poor. So just bear with me, be a little bit playful and accept that, we're playing a game. And okay, so there's 2 players in this game, A and B. These players are going to cooperate in order to win in the game. There's one restriction on them, which is that there's no communication. So they know the rules of the game and everything, but when the game starts, they can't talk to each other. So what's the game? In the game, each of them is going to receive a question, X for Alice and Y for Bob. And these questions are sampled according to the distribution pi. Okay, so X is an element of capital X, Y is an element also of capital X, and they're chosen according to the distribution pi, which is public knowledge. Alice get X, Pops get Y, and they have to produce answers. So A and B, these answers should range in the known answer set A, and their goal is to produce answers that satisfy the function D. So they will win if D of X, Y, A, B equals to equals to 1, okay? So their goal is to generate these answers that satisfy the predicate given their questions. In general, what games did, what may make the game hard is that Alice only has access to her own question. So even though she knows the question sets, she knows the distribution, she knows the criterion, she has X, but not Y. And so, determining a valid A might depend on what Bob got and what Bob is going to do. So she might know what Bob does, but she doesn't know what his question is. In general, given a game, we're interested in figuring out what is the best strategy and what is the maximum success probability of the players. Before I make this a little bit more formal, let me give you an example. So the example is called the magic square game. Let me try to fit it here. So magic square. So this magic square is parameterized by a square. So I'll just draw the square here. It's a 3 by 3 square, like this. So the questions I have to give you all the data there. What's x, a, pi, and t. So first x. So the questions take two forms. They can be either a line in the square or an entry. So I label them either L. So L will be either a row or column. Okay, so it means it's just a label. Okay, so there's 6 possibilities, 3 rows, 3 columns. I just named them, R1, R2, R3, C1, C2, C3, whatever. And then disjoint union of I, an entry in the square. And there's 9 possible entries. So just to make sure we get it, so the cardinality of the set X is 6 for 3 rows plus 3 columns plus 9 for 9 squares. So it's 15. Okay, so I label them in this way, but this doesn't really matter. The answers will take 2 forms. So for questions of the form a row or a column, I expect an answer that's a triple of values in plus minus 1, and for entries I expect just a value plus minus 1. So sorry, this is symbol for disjoint union. Okay, so these are the answer sets. Now, what's the distribution on question pi? You return an L and an I that's in L are uniformly at random. Okay, so to generate a pair of questions, I select one of the 6 possible lines at random, and then one of the 3 possible squares in that line at random that generates a pair. And then I'm not going to write it, but we usually symmetrize things. So the one that I call X and the one I call Y could be the line or the square or vice versa. Okay, and now the important part is the decision function. So D of L, I, A. Okay, so sorry, if one of the questions is a line, the answer is expected to be 3 bits. So I just write them A1, A2, A3, and B. And so this will be 1 if and only if, so in all the other cases it's 0. So when do you win in this game? So there's 2 conditions. One is that the parity of the 3 answer bits that's associated with the line should be a certain value that depends if the line was a row or a column. So A1, A2, A3 is supposed to be some number, alpha, that depends on the line, plus minus 1. And I'll write it on the picture. For the rows, we want plus 1, and for the columns, we want minus 1. Okay, so whenever your question is a line, you have to return 3 bits, and the parity of these 3 bits should be plus 1 or minus 1 if it's a row or column. So pretty, that's easy. And then there's another condition, which is that because I is an element of the line, this answer B can be identified with one of these answers. Okay, so we think of these, let's say, for example, the first row, I get as answers A1, A2, A3. I think of A1 as being here, A2 as being here, A3 as being here. Their product should be plus 1. If I was maybe the 3rd square, then B should be equal to A3. So I'll write it this way: B equals to A sub I. It's a little bit loose notation, okay? So these 3 are naturally associated with the squares in the line, and this value should change. Does anyone get the rules of the game? No?
I'm trying to get it. So if you get a line, you need to return 3 minuses, and B should be the entry.
No, if you get a line, you should return 3 values in plus or minus 1.
Yes,
like so.
3 minus or 3 plus, according to whether it's a row or a column.
Yeah, well, they don't need to be the same. No. So for example, here a valid answer is -1, -1, plus 1. Their product should be plus 1. So there's many possibilities, or -1, plus 1. Sorry, or plus 1, plus 1, plus 1 would be fine, but it doesn't need to be that. And the B, it should equal
whatever it is that
the other player returned. Yeah. So I'll write one more definition and then we'll maybe understand a little bit more by trying to check how well we can do in the game. So let's define the maximum success probability of the players in the game. I'll define it in this way. So I'll call it omega classical for reason that will come here a little bit later. So it's the supremum over, I want to write the supremum of all possible strategies of the probability that the strategy succeeds. Okay, so what's a strategy? So just to keep it simple at first, let's imagine that these players, the only thing they can do is they can apply a function. They have a question, they have to produce an answer. So fixing a strategy is like fixing a function from questions to answers. So I take the supremum over all functions for A and functions for B of the probability that this wins. So what's the probability that this wins? Well, I select questions X and Y with some distribution pi of X, Y. And then I'm summing over all answers. I'll put here B. So effectively, I'm only summing over valid answers, right? Because if this is 0, I'm just not counting it, of the indicator of the first player returning that answer and the indicator of the, sorry, it doesn't fit. I write it here. The product of these two indicators. So does everyone agree that, I mean, this counts, this here is, this product of indicators is 1 for a single pair AB if I fixed X and Y, and then I'm going to get 1 if this D is 1 and 0 otherwise. So this is my score for the pair of questions X and Y. Do I get valid answers or not using these functions? And then I'm summing over all questions and distributions. This is the probability that I give correct answers where the probability is taken over the choice of questions. So let's compute this for the game here. So maybe a claim that would help understand it is that there is no strategy that succeeds with probability 1 in this game. Okay, so let's try to.
Does it depend on pi?
I gave you pi. I gave you pi. Yeah. It does depend on pi, but I gave.
Sorry, no, I forgot you.
So we have to understand what's a strategy. Okay, so there's a strategy. There's the function for Bob and the function for Alice. These are functions from questions to answers. So parts of the strategy is a function. You have to decide, when you come up with the strategy ahead of time, if you're asked any of these squares, what are you going to say? Okay. So I have to say, okay, this square I would say +1, this one -1, +1, +1, +1, whatever, right? Some.
This omega class G, so just to understand, in principle, they could use a mixed strategy, where they have a probabilistic answers.
Yeah, so
this doesn't allow that, does it?
The definition, the way I wrote it, it's not clear that it allows it or not, but in fact, mixed strategies, probabilistic strategies will always be convex combinations of deterministic ones, and so these here I'm taking the maximum over extreme points, and so in fact it does capture. Okay, so to fix a strategy, I was trying to go over like what we need to say when we describe a strategy. So we need to give ±1 values for each of the squares. This is just what we answer on these questions. Then for each row and column, we need to fix 3 values for the row and 3 values for the 2 values for the row and 3 values for the column that have the right parity, and also that match the values that we gave to the squares. So it requires a little bit of thought, but if you want to succeed on every possible question, you need to have entries to the squares such that whenever there's a row, or a column, whatever assignment of signs you give to that column, it should product to -1, okay, fine, and it should equal the entries that you set your mind on for the squares, because if one of the players is asked that column, the other could be asked any of these 3 squares, and so whatever values it assigns to these 3 squares should match the 3 values that are assigned to the entire column, okay? So what this means effectively is that in order to succeed in the game, we're trying to fill in the 9 entries of the square such that the parity conditions are satisfied. That's the only way to succeed. And of course, it's not possible, right? Because, it's not possible. Okay, so we can't succeed on all possible questions, and then it's not hard to come up with a strategy that succeeds on all questions but 1. So you must fail on one of these, and the pi is uniform over its support. Its support has size 6 for the number of lines times 3 for the number of entries in a line. So that's 18, and you must fail on at least one of them. So this is equal to, okay. The strategies that sees on everything would, okay, whatever, there's many possibilities. Is this okay? Okay, so now, here's the reason I brought up this this game. The interesting fact is that the interesting point is that just like we did a little bit yesterday, we can broaden the class of strategies that we allow the players to execute. So this here, I can think of it as the probability that the players return A and B given X and Y. Okay. In this case, this probability is 0 or 1 because I focus on deterministic strategies, but I can write it in this way. So now I'll define another quantity, which would be the supremum. And now I'll take P to be in the set Q star here of N and K. So N and K now would be the size of the sets X and A of the sum over X and Y of pi of X, Y, the same thing. So sum over BP. So what this just means is that now I'm allowing the players to generate, given questions, generate a distribution on answers according to any family of distributions that has a form that's up there on the top left. You can try to compute this and actually we'll do a bit later. And so what happens is that in this case you get 1. So there exists a distribution in that set that gives you value. Okay. So I want to pause and make like a bunch of comments now. So one comment is that if we go back to this picture, if you remember last time, I had introduced also the classical set before even introducing the Q star, and there was also a Q infinity. This was a polytope, and it was a polytope that was here. So this we had called C classical. So if we've verified this equality that here it's equal to 1, then whatever P achieves or comes sufficiently close to 1 that it beats 17 over 18, that value there, it must be a P that lies that is here. Okay, in Q star, but not in the classical set. So by making these two computations, we've effectively separated these two sets. It's not the ones that we want to separate, but it's like a toy version. So where do these things come from? Non-local games in quantum information arose, not even in quantum information, I think in the foundations of quantum mechanics in the 1960s, their study, and they really came about as a way to resolve the EPR paradox somehow. So EPR wrote this famous paper in the 1930s where they were arguing about entanglement. So entanglement is a physical phenomenon that's predicted by quantum mechanics, and that seems to allow very strong forms of correlations between isolated systems. And then depending exactly how you look at it, you can get a little bit confused. You can say, okay, well, this correlation, does it imply causation? So is there really supraliminal signal? That can't be the case, that would violate relativity. But you try to come up with thought experiments that explain that, and that's what EPR did. And it can get a little bit confusing if you don't set things up properly. So in the 1960s, John Bell wanted to understand this, okay, what does it mean that quantum mechanics predicts that isolated systems can be correlated in a way that's stronger than classical intuition suggests, but at the same time can't possibly imply, supraluminal communication, because that just couldn't be the case. And this is his resolution. He said, okay, here's really what's going on. What's going on is that you can introduce simple game. Okay, so Bell wasn't talking in the language of games. This came afterwards. But you can introduce simple coordination games, such as the Magic Square game, that are asking separated parties to generate answers that satisfy a certain form of correlation. Okay, here the correlation is that the B should always equal to the A that matches it. And you can come up with games such that it's pretty easy to show that if you allow only classical strategies, so just like functions like I described here or probabilistic solutions, it's impossible to win in the game of probability 1. But if you model the strategy using quantum mechanics, so behind the definition that I gave here is really a quantum mechanical system. So you can, to these P's and Q's and this tau, you can associate a physical, like a quantum mechanical state that's a bunch of particles at A, a bunch of particles at B, and these P and Q's, they correspond to physical measurements that can be performed on these particles. And they will generate outputs A and B according to this distribution. That's written there. So Bell observed that there were games such as this, and the strong correlations of entanglement. This is what they imply. They imply that this is what they amount to. You can get a higher success probability using quantum mechanics than using classical physics. And this is not all theoretical. So you know, we came at this by studying a mathematical problem, but you can do experiments, and people do experiments, and they do experiments where this distribution here is generated, and you do the experiment many times, you check the statistics, and you see this one. So this is a very real, tangible thing that's going on there. That was my first comment. Questions on that? I have a second comment that's in a different direction. It's in the direction.
Physics this year was given for this experiment.
Oh yeah, you're right. Thanks. Yeah, I should have meant.
So we have a physicist in the audience.
That's important. Oh, that's a very good point. I forgot about that. Right. So there's a more famous, more well-known game. It's called CHSH game. It's more well-known because historically it came before this one, and it's a bit simpler. But it has a separation between these two numbers, and the experiments were done starting in the 80s, I think, up to like 10 years ago, where like all kinds of loopholes were closed, and the Nobel Prize went to the experiments from the 80s this year. Yeah, thanks. All right, yeah.
How many entangled pairs do you need?
We'll get to that in a second. So two in that case. So I'm actually going to prove that statement. So I'll tell you what is the strategy. I'll get to that before my next remark. So the other remark is that I want to start making the connection with this by observing that a game, specifying a game is a way to specify a linear form lambda. So here, this number like pi times d, I could call this lambda xy ab, okay? And if I call it lambda xy ab, then what this is just the sum of all x and y, a and b of lambda xy ab times the probability, okay? So it's exactly an object of the form lambda of p up there. So designing games is a way to design a linear function. So we're going to use this very heavily. Maybe just to tell you for a second where I'm coming from. So what we're going to be doing in the next is try to associate now not a linear function to a Turing machine, but a non-local game to a Turing machine, such that these statements hold. The way we think about these non-local games is that we think of them as proof systems. So given a game, the fact that it satisfies this equals to 1 is equated with the validity of a certain computational statement. So in this case, it's equated with the statement that the Turing machine halts. And if Turing machine halts, this value is 1. If it doesn't halt, the value is less than 1. What's the computational statement? Well, for example, here you can think of this magic square as a game that tries to check whether the system of equations that I have here, I have 6 linear equations in 9 variables, whether that has a solution or not. Okay. So that's my computational problem. Given the system of equations, is it satisfiable or not? And I can construct a game that witnesses it. The game is the magic square game. And if I look only at the classical value of the game, this classical value is less than 1, exactly because the system of equations is satisfiable. Okay. So this is something that you can do more generally, and you can start from any kind of constraint satisfaction problem and construct a game, associate a game to it, such that the constraint satisfaction problem is satisfiable if and only if the value of the game is 1. So these games are studied sort of like for themselves in complexity theory as proof systems. And the kind of computational problems that games capture when we think of them through, this is the measure associated to the game. This is well understood, but through some deep theorems from the 90s that characterize complexity of games from that perspective. The way I started on this is by trying to understand the complexity of games when you think of them as proof systems and with respect to this quantity here. And the statement of our theorem, MIP star equals RE, it gives an answer to that question. That's very surprising given what's known in this case. So it turns out that as proof systems, games are infinitely more powerful when you think of the strategies as being this kind of strategy as opposed to that kind of strategy. This is maybe a little bit vague, and it's not crucial for what comes next, but I just say it. All right, so back to the magic square. I want to do two things about it. I want to justify this statement and then make a kind of like a qualitative observation that is going to underlie why this game will be useful for us. Okay, so a definition that maybe I should have given before is what is a strategy for a game? So we have games, and then the other thing is strategy. Strategy is what the players do in the game. So in this case, so a strategy implicitly for a certain game, so magic square game or another game, is given by so I write it like this: S equals. And then it's going to have a certain dimension. So I just write it like this. And then it's going to have projective measurements PXA on CD. Okay. So the strategy says what is the underlying object here that generates the distribution that the players generate in the game, right? I could have said that strategy is the distribution, but no, I'm really saying what's the strategy is the thing that underlies the distribution. Okay, so let's have an example of a strategy. I'll describe a strategy that succeeds with probability 1 in this game. So it's actually very pretty. So we'll take d equals 4, so it's going to be a 4-dimensional strategy. And to describe it, I need to introduce some famous matrices from quantum information, the Pauli matrices. So they're just 2x2 matrices, very simple. This is one of them, and the other one is this one. So the only relevant facts about these matrices is that they're Hermitian, symmetric, they square to identity, both of them. And they happen to anti-commute. Okay, we can check that. Okay, that's the only thing that we know. Now I'm going to write them. I'm going to create a square out of these matrices. Okay, so bear with me. So I'll write. One here is the 2x2.
We don't care how big D is, do we?
I'm sorry?
Is that when you're saying you're trying to show us the strategy which gives 1, but there's no limit on D?
No, I could use any D. So I'm going to use this
case,
4.
4 is probably the smallest that works.
D equals 4 is the smallest that works. Yeah, we'll justify that after. Yeah. But in general, right, I wouldn't care. So these are all 4x4 matrices that I'm writing in the squares. Okay, and I'll just put a minus here. All right, so the relevant point is that when I take any 3 of them in a row or a column, they always commute. For example, in the first row, they commute because I only have x's. Here they commute because I have only z's. And here you can check that they commute. It follows from the anti-commutation relation. Also by columns, here these 3 matrices commute, etc. Okay, not only that, but if I take the product of them in a row, you can check that here I'll get +1 just because they square to identity. And if I didn't mess everything up by anything out by columns, the product should be -1. I mean, it's clear for the first column, it's clear for the second column. For the third column, it's also clear using the anti-commutation relation. So you just have that. Okay. So this is really what's going on in this square. I find it very elegant. So you all did in your heads the proof that there was no solution by multiplying all the entries and saying, okay, I mean, the product of all the entries has to be something, and it can't be -1 as it should be if I multiply by columns and +1 as it should be. Okay, and here this proof no longer applies because even though the matrices commute by rows and columns, like globally they don't commute, and so taking their product across all 9 squares, this has no meaning. So this is what makes that possible. Okay, let me not explain in too much more detail how using this you can construct a strategy. Basically, you use the spectral projections associated with each of these operators to construct the P squared strategy. So you have to construct PXAs of 2 forms, where X is a square, an I, and when X is a line. So to construct the one for the squares, it's easy. You just take the spectral decomposition of the matrix in the square. It has only ±1 eigenvalue. So you have 2 spectral projections, and these give you the PIs. To get the P's for lines or columns, look at the 3 matrices and you jointly diagonalize them, and this gives you the spectral projection. Yeah. Let me not give too many details, but it's easy once you've observed that to construct a strategy. Okay. You go over there. Questions on that? I want to say one more thing, which about this game, before going back to our proof strategy. Which is what Peter hinted, or in fact, slightly stronger statement. So first of all, we can show that any strategy in that game that succeeds with probability 1 needs to have dimension at least 4. Moreover, we can show that it must be basically unitarily equivalent to that strategy. Let me just give you a little bit, like a few lines about how we do that. So let's take let S a strategy that succeeds with probability 1. Okay, so the strategy is given by a bunch of projective measurements. So there's the PLAs, and then there's also the PI. Let's call them PIBs. Okay, so I have all these 16 projective measurements. I can define for every I can define yi to be equal to PI +1. So I'm doing the reverse of what I was doing over there, minus PI -1. Okay, so these are orthogonal projections that sum to identity. So this is just a Hermitian matrix that squares to identity. So I can write these y's in a square. So I can write it y1, y2, y3, y4, 6. Okay. And I can show, and that part I'm skipping, but I can show using the fact that the strategy succeeds with probability 1, that these y's that came from the strategy must multiply exactly in the way that I wrote here. So if I take the product of these 3, I should get +1, +1, where +1 is plus identity. But now this strategy can be in any dimension, right? I dropped the original one. The dimension could be, as far as I know, like 9 or 101 or whatever. In fact, it can't, but we'll see why. But so far, it could. So any strategy that succeeds with probability 1, from it, I can extract 9 Hermitian matrices squaring to identities that satisfy these product relations. That's the first step in the proof. Now, the second step is that we're going to show that necessarily y2 and y4 must anti-commute. I'll just show you that because it's very simple and nice. So I can write the product y2 times y4. Now y2, I can use the product relation of the first row to say that it's equal to y3 times y1. So I'll write it this way, y3 times y1. and y4 similarly is equal to y6 times y5. 6 times y5. Now 1 times 6, no, sorry, did I mess it up? I did mess it up, so I wanted to phrase it this way. 1, okay, y3 times y6, this is minus y9. So I would get minus y1, y9, y5, right? Now I can do the product in the other direction. Bear with me, I'm almost done. Y4 times y2, and now I'm going to use the rules by columns. So I can write this as y1 times y7 with a minus. And here it's going to be minus 5 times 8, 8 times 5, or 8 times 5. And I get the 2 minuses cancel, the 1 and the 5 stay, and 7 and 8 I get 9. So I get y9, y5, y1. Okay, so this is a minus y before. Okay, so the anti-commute. You can show that, and then you can show even more relations that are going to give you in the end that they must be equivalent to things of that form. But maybe I'm skipping that. The reason I wanted to show you that because this is a very important phenomenon for us. The phenomenon is that you can design a game. This game is called the Magic Square game. We designed it. This game forces any strategy that succeeds with probability 1 in it to have a certain algebraic structure. In this case, the algebraic structure is very simple. We just have some matrices that commute, the ones in the rows and columns, and some of them anti-commute. A nice consequence of anti-commutation is that it doesn't exist in dimension 1. Okay, so this implies that the strategy must have dimension at least 2, and you can work a bit harder to show that it has dimension at least 4. In fact, it must be a multiple of 4. This is the first step in designing games such that the success probability in the game might be 1, but the way to achieve 1 requires a certain level of complexity. In this case, the complexity is pretty low, it's just anti-commutation. We're going to build on that to design games that remain simple, but in order to succeed in them, you need to achieve more and more complicated feats in terms of the algebra that's generated by the projective measurements that succeed for probability 1 in the game. So that's the whole proof strategy. That's the reason I want to show you that example. This example is a classic example, but it's also a very important building block in what we're going to do next. I'm done with the example.
So when you say complexity, I know this obviously.
Right. So here it's
is it important that you have bounds in terms of how long things take, or how big D is in terms of anything, or is it more just this?
Here, there's no time. I could introduce many parameters to measure what I call complexity of a strategy. Let's just use the dimension as a proxy.
Okay.
So here it's important that I'm able to prove a lower bound on the dimension of the strategy. This will be used later on. Only that. We're going to continue.
So you didn't prove that 4 is minimal, you just said.
No, I didn't. Yes, I didn't prove it because it just takes like a few more lines.
Is there a principal bound on the dimension that you can compute from the game, or is it very hard to compute the dimension?
So a consequence of the results is going to be that there's no computable bound. If there was a computable bound, that given a game, you just stare at it, and in some finite time, you could say, okay, like for that game, I can win or almost win with this dimension, which is like 2 to the 2 to the 2 to the number of questions or something like this. So no such bound exists, because if it existed, then you could use it to, okay, these are lambdas, they're not games, but let's just like pause over that. You could use it to decide if the game has a value 1 or not. You would first compute this bound on the dimension, and then you'd just like create nets and like search over all.
Okay, but here's an important point. The first lecture was you assumed this conjecture to disprove it, to give a counterexample. Is this I can't remember what was the consequence which you would be. So he says it's not computable. That's assuming something, or
no. So right, okay. So thanks.
In connection with
our goal is to show this theorem. So the theorem is that there is computable function. This is not the important computability. The important one is in the halting problem. So we wanted to compute a reduction or a function that transforms Turing machines into games,
Right.
such that if the Turing machine
Yeah,
halts,
so that's a reduction.
that we want to complete that reduction. This is what this needs to be done. Once it's done, we'll have learned that this function is uncomputable. And
Yeah.
by what we did last time, it
Yeah.
gives it
Okay.
negates, it gives a negative answer. So I'm done with the example. Now I want to announce kind of like the next stage in the proof strategy, and we'll carry out pieces of that stage pieces of that strategy on Friday.
Let me ask you also about the theorems. So, would it suffice to show that the problem is in some lower complexity class?
No.
Say? RE is the minimal one.
So I'm actually not an expert in logic, but what was relevant here is that it should contain some undecidable problem.
So you couldn't have said that the algorithm you had that you produced last time with the inner approximation and the outer approximation lies in some even lower.
Oh, so we don't have any bounds on these. It's really only computable, especially the outer one, which I didn't give,
Yes.
but there's really no bounds on the convergence of that one. For the computer scientists, this outer approximation algorithm is a sequence of semi-definite programming hierarchies. That's what it boils down to. But there's no bounds on the convergence. If there was, then that would be, yeah, then we could use that. All right, so back to the theorem. So we want to prove the theorem. So I'm going to start like, like sort of oversimplifying things a little bit. Let me say what we're going to do. So we're going to show that, I won't show it, but our goal would be to show that there exists the following kind of transformation. So this transformation, I'll call it compress. Okay, so compress is a function. This function transforms non-local games into non-local games. And intuitively, what it's going to do is that it's going to reduce the size of the game. I didn't tell you how I measure the size of a game. Ultimately, we'll need fine-grained notions of size, but for now, just think of the size of a game as the number of questions plus the number of answers, something like this. So we're going to reduce the size of the game while maintaining its okay, I'll just say what we do. So it transforms games G to G prime such that the properties are going to be that the size of G prime is much smaller than the size of G. That's one important point. Another important point is that it's going to preserve whether this game had a perfect winning strategy or not. So if this was true, then the same is true G prime. Conversely, there's a prime here. I get sorry, bigger. So in other words, things that were 1 stay 1, and things that were below half remain below half. And moreover, some complexity parameter is going to be respected. So I'll write it here. So if the strategy S, this is an S, succeeds in G prime in the smaller game with probability bigger than half, then this strategy must have a high complexity. So the dimension of this strategy S should be at least some number. I'll write here, it doesn't really matter what it is, but 2 to the size of G. Okay, so the way to read that is that we reduce the size of the game. It's going to be smaller, so it's a simpler object as a game. However, the important parameter associated to the game is preserved. So if the optimum was 1, it remains 1. And if it was less than a half, take the counterpositive of that. If it was less than a half, it remains less than a half. And now the complexity of the original game G got transferred, not in the game G prime itself, which is simpler, but in the difficulty of succeeding in that game, in the strategies. So if a strategy succeeds in the simpler game, with probability that's bigger than half, then it must have a dimension that depends on some complexity parameter of the original K. Let me say a little bit why. So unfortunately, like if I had one more hour, I would give a more refined version of this that I would be able to show implies the theorem there. Now I simplified things a little bit. So be a little bit loose. Intuitively, the way this. There's a question.
Just a very quick question. Is the size just of G then the size of the sets A and N?
Yeah, so let me actually be precise. So I use N and I'm overloading my N. It's a bit terrible, but to say the log of the number of questions and K to be the log of the number of answers. I'm sorry, earlier it was the number, now it's the log. But, okay, so the size is N plus K. Okay, that's my definition of size. So now I'm being a bit rough, but the way that we're going to prove this is that we'll assign games to Turing machines such that these games at first are very complicated because the Turing machine can be a complicated object. In particular, the fact that it halts or doesn't halt is a very complicated statement. So we'll assign a game that's very complicated to the Turing machine. And then we'll iterate this procedure to make the game simpler while keeping the important statement that's there. I'm being very sloppy here because this is a non-computable statement, so I cannot directly create a game that captures that statement. So what's really used in the end is that this procedure is going to be iterated to infinity. We're going to refine this procedure a little bit and then take a fixed point of that procedure, introduce the Turing machines, and then create that. So that argument is a bit of an argument in logic that's not particularly new, but it's a little bit subtle, and so I'm unfortunately skipping it. And I kind of want you to believe that if we've managed to establish this kind of a procedure that keeps the game simple or keeps the linear form simple, but increases the complexity of the point that's used to witness this fact, the fact that the omega star is 1, then we're on the right track. All right. So now there's 3 steps that are used in order to achieve this. And I'll just say what the 3 steps are now and then end. And then next time, we'll focus on just one of the 3 steps that is going to involve some group theory arguments, some group stability arguments that I promised on the first time. Maybe before I say the 3 steps for the computer scientists in the audience, if there's computer scientists, the way we think of this is as a delegated computation procedure. So I tried to explain earlier why you can think of a game as performing a certain computation. And now I'm trying to construct a game G prime that's simpler. So the verification procedure is simpler, but the statement that's being verified is the same. So I'm delegated the computation that G was performing to the players in G prime. So only if you know about delegated computation, you could maybe follow what I said. If you didn't, it's okay. So here are the main 3 steps. I'll explain these 3 steps in the 6 minutes we have left. The first step is the most important one. It's the one that we'll go over next time. It's called introspection. Okay, what this step achieves is that it transforms a game G, so the game G, I'll just call it G0 now, into G1, and it's going to have the effect of reducing the number of questions in the game. So this parameter M will go down to much smaller compared to what it was before. The number of answers will remain roughly the same. So in fact, it'll increase a little bit. Sorry, there's no, I'm sorry. So this is an N. I changed notation. n is the log of the number of questions, and k is the log of the number of answers. So we'll achieve that, and all the other statements that are there. This one is going to have a similar effect, but now reducing the number of answers. So and the last step, I won't even write exactly what it does, but I'll explain it. It's called parallel verification. All right, so let me try to talk a little bit through these things. So we're trying to take games that have certain numbers of questions and answers and simulate them using games that have fewer number of questions and answers. We're doing this in 3 steps. So the first step has the effect of greatly reducing the number of questions, right, by a logarithmic factor essentially, and slightly increasing the number or the length of answers. It becomes the old length, but I added the length of questions here. The second step has the effect of reducing both the, what it really reduces is the number of answers, because here there's a logarithmic dependence. The number of questions can increase a little bit, but because we decreased it a lot in the first step, then it becomes small. So if you tag these 2 steps together, you can check that both parameters n and k got reduced by a polylogarithmic factor. The reason the third step is needed is that as you do these transformations, there's a little bit of a loss in the second bullet here. So it's not a half to a half, but it's more something like close to 1 to a half. So maybe let's say 3/4 to a half. So you loosen that, and that step is a classical step in computer science that has a mild effect on number of questions and answers, but it makes sure that these 1-to-1 and half-to-half are preserved. I don't want to talk too much about it. Maybe this is a good point to emphasize that this is, and maybe to Peter's question from last time, this is actually where finer grained, we won't actually see it, but where finer grained notions of complexity are needed. In a way here, I'm kind of like pulling a rabbit for you. In fact, no such procedure as I described could really exist. There is no miracle procedure that takes objects of a certain complexity and reduces their size while preserving the complexity. I mean, it doesn't make sense. In order for this A and B to be possible, we really need to look at more fine-grained notions of complexity. In particular, for these steps to be possible, it is crucial that I look a little bit more into how I represent a game, and I ask about the distribution pi and the decision predicate D. I just define them as a distribution and a function. It becomes very important whether this distribution and these functions can be generated efficiently and can be computed efficiently. This step is actually a classic step in computer science. This is the PCP theorem that maybe some of you have heard. The PCP theorem is a method by which you can take a proof for a certain statement and encode that proof in such a way that the proof can be verified by looking at not the entire proof, but only a few locations chosen as random. This cannot be done in general. This can only be done for proofs that have efficient verification procedures. So only when the proof is such that there exists a circuit, an efficient procedure that verifies the proof, then I can encode the proof in such a way that there is a more efficient procedure to do it, where the procedure is randomized. So here, in order to carry out that step, it's going to be important that the function D that I used when I defined the non-local games, that function D can be computed efficiently. Only thanks to that will we be able to reduce the number of answers here. Similarly, here it's going to be important that the function D can be computed efficiently, and also there's going to be some restrictions on the distribution pi that can be used. So the restrictions on the complexity of the function D, they won't show up. I'm going to sweep that under the rug. The restrictions on the distribution of questions, these will actually, I'll be able to explain them on Friday. So on Friday, we'll go into a little bit more detail into that step A, which is really the important innovation in the work. And if you think about the magic square game, like a sub goal of that procedure will be to design games whose size remains constant, but such that the complexity of strategies that succeed with probability 1 in the game increases and increases and increases. So we're going to be trying to design games that enforce relations on the algebra of measurements of a successful strategy that are more and more complex, so that these strategies need to have higher and higher dimensions. And we'll do that by kind of like embedding groups into the algebra of measurements. Yeah, so I think it's time to stop.
Thanks, Thomas, for a wonderful lecture. And questions also from the Zoom. If you want to ask a question, just unmute. We'll hear your voice. I'm usually coming from there. Questions? Yeah.
I have a quick question. I think you mentioned this a little bit, but could you go over how are you going to use this compressed procedure in the reduction that you're going to do from the halting problem to the W problem?
Say the question again, sorry.
So
how are we going to use this?
So like you're defining this compressed procedure. If you have like one of these games, you can like reduce the size of the game. How are you going to use that to then, how is this going to play a role in the reduction that you want to ultimately do to prove the theorem?
Yeah, so this requires a little bit more work to answer. So my real goal is to define this game here. So I'm starting with a Turing machine and I need to define a game. That's the only thing I need to do. So check this. Things are satisfied. So this game associated to the Turing machine is going to be defined as the fixed point of a procedure that involves compress. So I won't actually show that. If you want, we can take time. I can show you it like in half an hour. I can show you, but not in 1 minute.
Yeah, he's here for the week, and he's supposed to.
How does
Sure, he will answer any questions that you want to ask. And we're going to lunch afterwards also.
How does it make it compute? I mean, you want it to be computable, right? How does it
Uncomputable?
You want to have a computable function from Turing machines too.
Yeah.
But how does having this compression make it computable? I assume that's about.
No, so this compression is a computable function, and fixed points of that computable function are also computable. You can write down Turing machines that return fixed point.
Yeah.
So here we're designing a lambda or a game for this omega star. If we were to design for omega class, then which of these 3 steps could still be done or none of them? Just B could be done. So it's really A. I guess C could be done too. So A is really the thing where it's quantum. So it's,
yeah.
So let me repeat my favorite question. When you say in B, you really need the PCP theorem in the form of a complexity polynomial. That's necessary in the proof. So
it's necessary in the proof. I can't say that it's necessary in the absolute, but it's necessary in the proof. Yeah.
Okay. Yeah. So that's.
You think the way this comes about is that you think of these answers in the game that come back to you as a proof. In a way, they're a proof that this game can be won or something like that, right? So you think of them as a proof. And now you want to create an equivalent game such that the proof is shorter. So you want a proof for the same statement, but it should be shorter.
And the polynomial enters into the verification.
Yeah, the way you're going to achieve that is you're going to leverage the fact that the way the proof was verified was using a polynomial time procedure. And using that, we can apply the PCP term. If we didn't know that, we couldn't apply.
Okay, so that really answers the question. If you're at the Institute and you wanted to talk about introspection of such a move, it was once called here in another context, endoscopy. So Langland's when he was trying to formulate a notion in trace formula where you introspect the formula. He went around and asked people, and there was somebody whose wife was a medical doctor and said that That kind of introspection is called endoscopy.
I can ex-
So
I-
lecture
I-
3 will be endoscopy.
I'll explain, let me explain because it's literally, I'll explain the term next time.
Okay.
What this particular one means and then we can.
All right, maybe.
This one is really introspection.
Okay. Not internal.
Yeah.
All right. Well, thanks for a wonderful lecture. I hope everybody comes back and board to see the third lecture where everything's put together and introspection is explained. Thanks.